Okay, in this video, we are going to talk about topology. So topology is our tools, some definitions and some tools that hold for general metric spaces. So they include the norm and inner product spaces that we'll talk about later. But they're general enough that they hold for more than just norm and inner product spaces. So there's a lot of definitions, and we really need some of these definitions to get through. Chapter 2, there's just lots of definitions, and we need some of these definitions so that we can formally talk about things in the future and know exactly what we're saying. Okay, so here's some definitions. Given a metric space, remember a metric space is a set of objects x and then a function d, which is a distance function or a metric that measures, in essence, the distance between objects in x. Okay, so given a metric space xd, a delta ball around xd, so in other words, delta is going to be a small positive number. So we're going to talk about a delta ball. This is what we're defining is a delta ball. A delta ball around x naught is defined to be this set. Oh, yep. I have a typo here. So it's this set B x naught delta is going to be the set of all little x's in our bigger space such that the metric, the distance between x and x naught is less than delta. Okay, so for example, if we're in R2 and we're just doing the normal distance, then if we have some, x naught, then we're going to look at all of those vectors that are less than, this distance here would be delta. So it's a delta ball. So it's a ball of size delta around x naught. Exactly what it sounds like, okay? But this is in general, whatever x we picked, or whatever space we have here, so the set x and metric, we can define a ball around x. Okay, second definition then is that of an interior point. So we say that a point x naught in this set x is interior to S. In other words, S is going to be a subset of x. So here's our bigger x, and then S is some set here. So we say that that x is interior to S if there exists some. Oh yeah. Now here's another notation that we need to define. This symbol here is there exists. There exists. Okay, so if there's, there's kind of these two, for every, this is for every element of x, and then there exists, exists one. In other words, there's one element, there exists a delta greater than 0, such that the delta ball around x naught is an S. So we say that x naught is an interior point. Here's x naught. If there's a delta ball around it that is all inside of S. So in other words, if you have, a point right here on the boundary, then there's no delta ball that around that point that is entirely inside of S. So that's why we talk about it being an interior point, right? It's an interior point if you can put a delta ball around it, and that delta ball is still inside of S. So for example, if you have on Rn an open subset, 0 to 1, this open set is going to be, I guess we are going to then define a, maybe I'll talk about that example here in just a second. We now have a definition of an open set. A set is open if all of its points are interior. So for example, if we have, we look at this open set, 0 to 1, this is the set of all real numbers between 0 and 1, but don't include the endpoints. So how do we know that this thing is open? Well, any point inside of here that's inside 0, 1, can we does there exist a delta so that the interval around that point is all inside of 0 and 1? And no matter how small you get, no matter how close you get to 1 here, there's always going to be a space between that point and 1 because we don't include 1, you see. So there's always going to be a little space. So we could always pick however much space in there, we could pick delta to be half of that. And the interval around that point is going to all be inside of 0 and 1. Now, as soon as we include an endpoint, so if we do 0, 1, square bracket means we include 1. 1 is part of the set. Then, once we include 1 here, there's no delta ball that is all inside of this. So this set that includes the endpoint is not going to be open. Okay, so an open set is one in which all of the points are interior. In other words, every point in that set, you can put a delta ball around that point for some arbitrarily small delta. Okay, now we can conversely define a closed set. So a set is closed. A set, I guess this should be a set S, is closed in X if X, and this, this notation here is set minus. So this is the set X minus the set S. So in other words, I have, here's X, and this is S, and so X minus S would be this set. This would be, X minus S would be the, okay, so we say a set S is closed if when you do that set minus S, this set out here is open. So again, on the real line, if we do the between 0 and 1, let's say, so the interval 0 to 1, and X, this would be S, and R, or X is going to be all of R, then X minus S is going to be the set minus infinity up to 0, union, 1 up to infinity. And notice this guy is going to be open because I can, it's all of this stuff. And any of those points are an interior point because I can form a delta ball around them, arbitrarily close to the boundary, but not including the boundary. So this set S then is going to be closed. All right, so now that we have talked about open sets and closed sets, we can talk about convergence. Okay, so convergence again is defined for metric spaces. So if we let XD be a metric space, then we say, you can think of this a sequence, XN, n equals 1 up to infinity, where xn is all in X. So, visually you should be thinking, okay, here's X, and I've got, here's X0, X1, X2, X3, X4, I'm just marching along. So these are points in my set. And remember, if it's a function space, these are functions, a sequence of functions. If they're just vectors in R2, they're just, elements of R2 or whatever. So we can say that this sequence converges. Okay, so the following statements are all equivalent. We say that, if you take the limit as n goes to infinity of xn, if that equals some point x star, And xn, we could also write this arrow, xn converges to x star. And what do these things mean? It means that for every epsilon, this is for every epsilon greater than 0, there exists some number at n such that when little n is bigger than capital N, the distance between xn and x star is less than delta. Okay, so let's go back up here. We've got our sequence, and let's say there's some element here, x star. So this is saying for every epsilon, you pick any epsilon, okay? And I'm going to okay, this statement is, this should be epsilon here. Okay, so for every epsilon, I look at this epsilon ball. I could have put I guess I could have put a delta over here. But okay, so I have every epsilon. There's going to be some n. So this is 0, 1, 2, 3, 4. At some point, there's some number, maybe 100, 150, so that when little n is bigger than that, so I get bigger than 100, I'm inside that ball. Okay, and I stay inside that ball. So that every n that's bigger than capital N, this is true. Okay, so when it converges, it says I can pick any epsilon. And so, in other words, and it's for every epsilon. So when epsilon is equal to 0.1, then maybe when epsilon is this small, maybe n is equal to 100. Okay, but I can pick epsilon even smaller, 0.001. Now I've got a smaller ball. And so in that case, n is probably maybe 1,000. Or if I pick, 10 to the minus 15, then maybe n would be, 10 to the 10 or something like that. So this says for every epsilon, I can pick any epsilon you want. So I can get arbitrarily small or close to x star. For every epsilon, exists an n, and the n is going to be a function of epsilon. Because when epsilon gets smaller and smaller, n is going to get larger and larger. So for every epsilon, there's some n, so that when little n is bigger than that capital N, then I'm within that ball. So we say that the sequence xn, a sequence xn in x with a limit x star in x is said to converge. So these things may all be true, but x star has to be, for it to converge, we have to say that, this last condition, x star, the thing that it's approaching, getting closer and closer to, that thing actually has to be inside of our set x. Okay, so just a comment here that limits may not always exist, just like a minimum or a maximum don't necessarily exist. And so, for example, think of sine of t. Sine of t, there is no limit, right? This thing, it just goes up and down. So the limit as t goes to infinity of sine of t, this does not exist. So in the same way, we can define something called the lim sup and the lim nth. So this is basically, the lim sup is the largest limit of any subsequence. So the lim, the lim sup of sine of t is equal to 1 because there's a subsequence. See, there's the subsequence tn that converges to 1. So in other words, there's a sequence here. So it's, it's for any subsequence. It's the largest limit of any subsequence. So if you can pick a subsequence that converges to something big, like 1, and in fact, you could pick them exactly at this point, and that converges to 1. That's going to be the lim sup, and the lim inf is the same thing. There's, it's the smallest limit of all possible subsequences. Okay, so a lot of times we'll use lim sup and lim inf instead of instead of the limit. Okay, now let's move to a topic that's quite important to understand and at least to know sort of what's going on here. And it's really a conceptual. We can do computations with Cauchy sequences, but really it's a conceptual idea. Okay, so we're going to talk about this idea of a Cauchy sequence. So we have this sequence, xn, n equals 0 to 1 to infinity, in a metric space. It's said to be a Cauchy sequence. So this is what we're defining, a Cauchy sequence. If for every epsilon, there's some n, and it could be a function of epsilon, so that when little n and little m are greater than capital N, the distance between xn and xm is less than epsilon. So notice here with a Cauchy sequence, we're not talking about a limit point. So there's no x star here. So what we have instead, this might be our set x, and now we have this sequence, okay, and it's getting like this. And what we're saying is that for every epsilon, so you pick an epsilon, there's some n after which the tail is getting closer, after which when you pick any m and n, so n might be, let's suppose that epsilon is 0.01, then that might be, for this particular sequence, it might be that n is equal to 1,000. Okay, now if I pick n equal to 1,001 and m equals to 1,002, then I have to be within this ball. But if I were to also pick, this to be 10 to the 5th and m to be, 1,050, that those two, epsilon or xn and xm are going to be less than epsilon. So in other words, the tail, basically what a Cauchy sequence implies is that the tail is getting increasingly closer together. But notice again, we haven't said anything about an element of convergence. There's no x star. So that's an important point, because Cauchy sequences may not necessarily converge to an element inside of X. So we can have a sequence in X converges. Yeah, here's a theorem. If the sequence converges to X star, then it's Cauchy. So if it's converging to X star, then it's a Cauchy sequence because it's getting closer and closer to some X star, so all the tail is getting closer and closer together. But the converse is not true. In other words, if it's a Cauchy sequence, it may not necessarily converge to some X star. And a simple, the example that people use all the time is, for example, if my set X is equal to 0 to 1, so the open set 0 to 1. Now look at the, and my metric is just, let's suppose the metric is equal to between x and y is the absolute value of x minus y. So x is, again, this is a metric space because x is a set, and then we have a metric. The set doesn't include all of R. It may just include a part of R, in this case 0 to 1. Okay, so now let's suppose I have a sequence. xn is equal to 1 over n. Okay, so when n is equal to 1, and this could actually be n greater than or equal to 2 or something like that. So it starts at a half, and then it goes to a fourth, and then an eighth, and then a 16th. Okay, so xn it's getting closer and closer to 0. And in fact, you can look at the distance between xn and xm, is going to be 1 over n minus 1 over m. And for any epsilon, you can always pick an n so that these things bigger, it's getting smaller and smaller. So this sequence is Cauchy. This is a Cauchy sequence. Okay, but if it was in all of R, it would be converging to 0. You see. So if our bigger set X was R, then XN would converge to 0. But 0 is not in, X equal to 0, 1. So XN, doesn't converge in X. Okay, so this is a very subtle point. It's actually converging to something outside of X. And so we'll see that, in fact, metric spaces where this happens are in some way they're defective, because we have these converging sequences that converge to something that's outside of the set. Okay, so another example. This is from the book. If we have the set of continuous functions between -1 to 1, so this might be -1, this would be 1, and I look at all continuous functions, and then you let the metric be the integral of the two norm. So you take the difference of the two, integrate between -1 to 1, take the square root. So this is a valid metric. Okay, now you can actually, if we define Fn now to be this function that is 0 up to -1 over n, and then linear between -1 over n and 1 over n, and then 1 after 1 over n, then you can find that the integral of the difference between Fn and Fm, this is Fm and Fn and Fm, is going to be this function. And, because you've got a higher order on the bottom than you do on the top, for, this thing goes to 0 for n and m large. So for any epsilon, you can pick a capital N, so that when m and n is bigger than that, this is less than epsilon. So it is a Cauchy sequence, i.e., Fn, this thing is Cauchy. Okay? But it converges, clearly the thing it converges to is going to be a discontinuous function. So it's going to converge to something that's, looks like this right at 0. And so it's converging to a discontinuous function, which is not in, this thing is not in our capital X. So again, this set X, this metric space that consists of the continuous functions and this metric, is in some way defective, because we can have these converging sequences, or these Cauchy sequences, that don't converge to an element inside of that function. All right, so that leads to the definition of what we call a complete metric space. So this is a very important idea. So we say that a metric space XD is complete, okay, if every Cauchy sequence in X converges to a value inside of X. In other words, if we don't have this defective situation where we have these sequences that are Cauchy, but they don't converge to something inside of X. So, for example, this metric CAB, CAB with the metric, this would F minus G squared, the 1/2, is not complete. Also, the set, if we look at the set, 0 to 1, where that's X, and then the metric being the absolute value, that is not complete. Okay, so in some sense, this is a defective metric space. Now, if X was all of R, and we use the same metric, then it is a complete space. All right, so later on we'll talk about norm spaces, And we have something that's a Banach space, our complete norm spaces. And then we'll talk about inner product spaces, and Hilbert spaces. This is where we'll spend most of the time this semester, are going to be complete inner product spaces. So these these spaces LP and big LP and little LP are complete, or they're Banach spaces, and then capital L2 and little LP L2 are going to be Hilbert spaces. All right, so we'll have more to say about that later, but there's this notion of complete Hilbert, a complete metric space where every Cauchy sequence converges.